Hi, everyone. I can't be with you today. I hope you had a good weekend. My wife has COVID. And so if I happen to get COVID from her, then I may not see you uh, all week. Who knows? But either way, you still have to be responsible. I hope that you'll keep up because we don't want to slow down our pace with chapter 7. I want to finish chapter 7 as best as we can. And so we can enter chapter 8 and finish this year strong. Uh, so we will continue with our lesson on chapter 7.5. You may recognize this sheet. This is the sheet I gave you last week. So if you want to take that out, that would be great. I'm going to continue on, sort of remind you of what we have done so far. And that is to graph two different exponential functions just to show you the general shape that exponential functions take, so that anytime you see something like this, you'll be like, oh, I'm dealing with something to the power of x. Okay, so that would be 2 to the power of x. And at the same time, let's see if I can change its color. Maybe I'll do a red. Boom, bam, bam. Something like this. Okay, and that would be half to the power of x. Okay, we talked about that. We talked about the domain and range. That stuff right now is not too important. My goal for today is essentially get you comfortable with the exponential function and have an understanding of how we can change the function by, multiplying the actual power by a coefficient, by adding something. And if that looks familiar, it is because it essentially is a transformation of a function. In the past, you have already transformed for me a parabola. You've already transformed for me a sinusoidal. And so you'll see the stuff happening again. But we are going to simplify it. There's only going to be so many ways that we transform a exponential function, because most of the time, at least in our, I guess, what we expect in the near future, you won't have to worry about too much besides these two variables, the a and the c, okay? Another thing that I need you to do today is to recognize through a table of values whether something is an exponential function or not. And so I'm going to give you an example, all right? So let's worry about the transformations later. I think this might be easier to grasp. You may remember from grade 9, grade 10, something called first difference and second difference. Essentially, we are doing a difference, in other words, a subtraction. And what that helps us do is identify whether something is a linear, so first difference, or a quadratic, second difference, or so forth. You'll see something interesting happen. So just to recap, if I have all the numbers in the first differences, when I subtract all the y values correspondingly, and they all happen to be the same name, then I know that y equals whatever this equation is, x has to be the power of 1 because it's first difference. If this doesn't work out, and then I happen to subtract it again, and it just so happens that all of the numbers I get in the second column, aka the second difference, is the same, then I know that the equation is y equals something where x is to the power of 2. In other words, this is a straight line, it's linear, and this is a parabola, so it is quadratic. At this point, you'd be like, I don't remember anything. That's fine. Take a look at this. Hopefully this is a refresher. Let's start with the easy one. How to do a finite difference. You literally take the y value of one, I guess, coordinate point, and then subtract it from the previous. And that would be a 1. Let's do it here too. Take one of the y values and subtract it with the previous. So take the 4, subtract it with the previous. That's a 2. And then 8 is subtracted by a 4. Well, I get a 4. Let's keep going anyways. I already know that the first differences are not the same, but just to fill this chart, I'm going to keep going. 1 is subtracted by half, or 0.5. The answer is half, or 0.5. half is going to be subtracted by a quarter, and that's 0.5 minus 0.25. The answer is 0.25, or a quarter. And if I take 1/4 and I subtract it by 1/8, the answer is, well, you might have guessed based on the pattern, 2, 4, 8. So take a look at the first differences. Does that look consistent to you? Does that look constant? Is it the number all the same? The answer is no. So I know for sure it's this data right here is not going to be linear. So let's explore again. Let's try second difference. So you take the numbers from the first difference and you subtract. That's a 2. 2 minus 1, that's a 1. 1 minus half, that's a half. Does that look familiar to you? Half minus 1/4, 1/4, and 1/4 minus 1/8 equals 1/8. Does that look familiar? If you look at the left data, it went from 8, 4, 2, 1/2, 1/4, blah, blah, blah. 4, 2, 1/2, 1/4, blah, blah, blah. 4, 2, 1/2, 1/4, blah, blah, blah. It keeps on repeating. Am I getting anywhere? Would I get anywhere if I subtracted it again for a third difference? Probably not. So this data does not represent a straight line. It does not represent parabolas. Instead, I'm going to show you something interesting. Instead of subtracting, I want you to try dividing. Create a ratio by taking one of the y values and dividing it by a previous value. So let's do this. 8 divided by 4. 2. 4 divided by 2. 2. 2 divided by 1. 2. 1 divided by half. And if you do that right, you'll probably would have guessed it is a 2. Okay, 1 divided by 0.5, you can put 0.5 twice. Next one, half is divided by 1/4. It's going to be a 2, and so on and so forth. They're all the same. In situations like that, where the ratios are the same, that gives you a very good hint that this is going to be exponential. Now, of course, there's a lot more to it. It's not always this easy, but it's just a very strong clue that it is going to be exponential. Exponentials being a little bit more complicated than just finite differences. Again, first ratios is not the best indicator, but I wanted to show you that there is a relationship that does technically exist. So look at that arrow. It says exponential functions will provide constant first ratios. Okay, and I'll put a little disclaimer on that. That concept could change a little bit as you further your knowledge in mathematics, if you choose to do so. So put little asterisk there saying more to it. I don't know. Okay. So again, the first question that you're going to be asked is for homework is, hey, take a look at this data and tell me if it is linear. So that's first difference. Tell me if it is quadratic. That's second difference. Or if it's exponential by doing ratios. And then you justify your answer based on that. Okay. Now, putting that aside, so you can put little notes wherever you need to remind yourself this is how you check for first, second, or first ratios. I want to, knowing that that's what you're going to be doing for number 1, I want to go through observation 2, in other words, the different transformations you can do by doing an example. If you remember for parabolas, I hope you do, y equals x squared. A parabola could be transformed at our level, having a number in front, multiplying, having the x value subtracting by a number, and then all of that is going to be added. Do you notice a similarity with the A and the K, with the A and the C? Yeah. That A, which represents a vertical stretch or a compression or a reflection, also apply here too. Stretch, compression, or reflection. That K value, which represents a vertical shift up or down, also apply here, a vertical shift up or down. The H value, which moves or shifts the parabola left or right, could also apply here, but it's rarely seen in our application question, so I'm not going to introduce it at the moment. Okay, so let's talk about some of these values. Normally, an exponential function has a y-intercept of 1, and it does something like this, and it approaches a 0, of course. If I were to vertically stretch it, you could do that. If I were to vertically compress it, it could do that. Okay, so that number could definitely change how quickly it rises or how slowly it might rise. Okay, what you call it? Yes. What's interesting about this exponential function is that the vertical shift affects the graph a lot more significantly than you might think. So I have my normal exponential function. If I have a c value of, let's say, 5, the entire function vertically shifts 5. 1, 2, 3, 4, 5. It's going to look something like this. So what happens to my asymptote? It used to be at 0, but if I vertically shift 5, then my asymptote, which used to be y equals 0, is now y equals 5. What does that mean? Well, the main significant thing, I think, my y-intercept was a 1, but now my y-intercept was a 6. Where I cross the y-axis when x equals 0 will depend on that c value. Now, again, you might not have any idea what the heck I'm talking about, so let's take a look at this. Here's a question that I may ask sometime in the future. It's very important. Take a look. I give you a bunch of transform functions. I'm going to ask for the y-intercept. I can ask for the sketch of the function based on your transformations. And using that sketch, you can tell me your domain and range. And then, of course, identify where the horizontal asymptote is. Okay, let's try it. We'll do an easy one, and then we'll do a super hard one. First one, let's do an easy one. Y equals 3x. So let's do that. Just to keep things simple, because I know where the asymptote might be, I'm going to do -1 and then 0, 1, 2, 3. Let's start off with a table of values. 3 to the power of 0, anything to the power of 0 is 1. 3 to the power of 1, 3 to the power of 2, 3 to the power of 3. There we go. And if I go backwards, you see that the number is getting smaller and smaller. I'm actually dividing it by a 3. I know it's going to be 1/3. That has a y-intercept of 1. Check it out. Area highlight. Okay, has a y-intercept of 1, 0, 1. And it's going up really high, really fast. Yeah. So determine the y-intercept. Hey, the y-intercept means that the x value is automatically a 0. So for this one, I know that the y-intercept is 0, 1. No change. Part B. Sorry. Part B. Sketch the function. Well, I did. That's a 1. That's a 3. If that's a 2, that's a 9. If that's a 3, that's a 27. Okay. State the domain and range. Domain, just like we did on Friday, it can be anything. For the range, it looks to me that it can go up forever, but it cannot cross that y equals 0 asymptote. So y belongs to a real number, but y has to be bigger than 0. And then lastly, state the equation of the horizontal asymptote. There is no vertical shift, so y is just equal to a 0. Okay. Now, even if you weren't able to follow all of that, again, you could watch the video again, but with some extra careful time and some dedicated homework practice, you should be able to figure that out sooner or later. But sometimes it can be a little bit more confusing. So let's step it up a notch and do letter E together. Do letter E together. Selecting annotations. I'm going to erase all this. Yeah. I know I might have been moving fast, but you can always check the video later. I'm going to do y equals 2x minus a 3. What does that mean? Well, my normal function is going to be 2x, but then I have a vertical shift down of 3. So I'm going to expect something like this. It used to be like this, and then I go shifted down by 3. It's going to be something like that. Right? So that's what I'm going to expect. Here we go. Is there a way to draw this very carefully? Starting off, I know that when x is a 0, my y is a 1. When x is a 1, it's a 2. When x is a 2, it's a 4, so on and so forth. This is my base or parent function, 2x. All of this is going to vertically shift down by 3. So 1, 2, 3. Maybe I could do a different color. 1, 2, 3. 1, 2, 3. 1, 2, sorry. 1, 2, 3. And then so on and so forth. And I could draw all the left side, but I'm a little bit lazy. I'm actually going to use my asymptote knowledge to my advantage. I know there's going to be a dotted line, and that's going to be shifted 3 down as well. So 1, 2, 3. My dotted line is at y equals 3. So I know it's going to approach that 3 line or -3 line, and it's going to hit these 3 dots. So I'm going to eyeball it and use my general math knowledge to make that a reality. So there, my red line is my sketch. State the domain. Once again, for domain, anything goes. There's no restrictions whatsoever. For range, however, it looks like it's going up forever, but it also appears that it will approach -3, but never go past -3. So y belongs to real numbers such that y must be greater than -3. Why is that -3? Well, that gives you a hint of what the equation of the horizontal. As you try to attempt, I think again, I'm going to put a little star next to number 2. Okay. I highly recommend you try, because I think it'll be very good practice to graph and take a look at an equation and know what it might look like. Some of you might still have no idea what the heck happened, right? When I'm trying to do this. So here is my recommendation to you. When you are applying this, literally, every single one of these, you can start with a table of values. So let's pretend you're doing a hard one, right? Y equals 4, 0.5, x plus 5. Just start with -2, -1, 0, 1, 2. And if you need more points, just do 3, 4, and just solve it. plug in a -2 here, plug in a -1 here, plug in a 0, 1, 2, 3, 4, and start getting your y values. And then you will start to plot it. Something like this. Okay, you'll start to plot and you'll start to see where the asymptote is. You'll start to see where the y-intercept is. It'll be right here, right? You'll start to see this and that. If there's any question you're going to do in this homework, do number 2. Start with A, even though we did it together. Start with your table of values. Start solving like crazy because it's going to be very important. Okay, and that's it for the remaining period of time today. Do not go home before you finish number 2. It's super important that you do. Try number 1 because that gets you to practice your first difference, second difference, and first ratio. And if you are feeling more inclined, we have number 3, which gets you to look at a linear, a quadratic, and then an exponential, then comparing and contrasting. And then comes to number 4, which is your final test. If I gave you the equation, knowing generally what an exponential equation looks like, what a parabolic equation looks like, what a linear equation looks like, can you match it? And something like this is an amazing multiple choice / diagram question for the test. You have been warned. Do your very best, and hopefully I'll see you tomorrow. Study hard.